Hello everyone, today we'll continue going over the AWS question bank. Next, let's look at question 6. This question mainly concerns NFS. We need to deal with content related to NFS. Specifically, we need to transfer 70 terabytes of video files from NFS to an Amazon S3 bucket. The requirement here is to use as little network bandwidth as possible. The key point is that as little network bandwidth as possible actually means we should avoid using the network for the transfer if we can. Because with 70 terabytes, no matter how you look at it, if you transfer everything over the network, the traffic and bandwidth required would be enormous. Plus, when transferring over the public internet, your bandwidth cap is only so high, right? The maximum network speed is actually quite limited, very limited. So first, let's take a look at the options. The key to this question actually lies in minimizing network bandwidth. For option A, it suggests using the AWS CLI to copy directly over the internet. 70 terabytes, right? Just copy it slowly. That won't work, right? It's way too slow. If you copy directly over the internet, transferring 70 terabytes would take forever, so option A is not suitable. Option B suggests using a Snowball device. We've talked about Snowball in previous questions. What is it? It's a physical data transfer device.
If you want to learn Kubernetes technology or get the CKS question bank, please send me a private message. You can also leave a comment below the video to discuss technology.
So how exactly does this process work? First, AWS ships the device directly to us, and then we proceed to upload our data onto it. The next question is, how fast is it really? At the very least, it's significantly faster than utilizing conventional USB drives or even external hard drives. Even if the actual transfer speed were only as rapid as a standard USB drive or an external hard drive, it would still prove to be considerably faster than transferring data directly over the public internet. Furthermore, when we meticulously copy valuable data onto a physical device, there are absolutely no bandwidth requirements or inherent limitations involved. It's only as fast as your specific storage device can efficiently read and write information. The transfer is extremely fast, so option B actually meets the requirements, right? It doesn't use any bandwidth, and the speed is very high. As for option C, transferring over the public internet via a file gateway and then ejecting it after the transfer, it's still using the public internet. Since it mentions the public internet, it will definitely consume a lot of network bandwidth. Option D is direct connect dedicated line transfer, which is indeed faster, but it still depends on network bandwidth. With 70 terabytes of data, you can't avoid that. No matter how fast the speed is, you still have to transfer that much data out. So here we should choose option B. The seventh point is about an application. Now, there is an application actively receiving numerous messages, and dozens of other applications and various microservices urgently need to consume them very quickly. The current consumption rate can be significantly increased to approximately 100,000 messages per second, which is indeed a truly huge volume of data. Now, the company specifically wants to utilize a robust geo solution to substantially improve its overall scalability. So, which particular solution is more suitable for this complex scenario? First, let's carefully look at option A. Option A is to reliably persist these important messages within our dedicated service, and then here. This service is mainly used for what? It's used for real-time data stream analysis, such as SOGO query cases, rather than as a general-purpose message distribution system. Therefore, it's not very suitable, as it can't allow dozens of different consumers to process messages independently. As for option B, it expands the receiving application by scaling out the number of ECL instances. So, what does this actually solve? It mainly addresses the scalability issue on the ingestion side, but it doesn't solve how to efficiently deliver messages to dozens of consumers, so it's not quite right either. Now, for option C 2.0, it uses our single shard. Here, several different services use our single shard and our database. The single shard can handle high throughput messages, and in terms of message processing, that's not a problem. However, if it's a single shard, the throughput is limited to the maximum of a single shard, which is about 1 megabyte per second for both input and output. It can't handle 100,000 messages per second, right? The size of 100,000 messages per second is definitely much larger than 1 megabyte, so this option is also not suitable. As for option D, it uses SNS topics and multiple SQS queues, so this is actually a classic fan-out pattern. SNS serves as the message publishing hub and is highly scalable, right? It can easily handle burst traffic. Each consumer can also have its own SQS queue, and by subscribing to the SNS topic, each can independently receive a copy of all the messages. In this particular way, it actually achieves a perfect and complete decoupling. The producer, in its role, only communicates directly with SNS, while the consumer, on the other hand, only communicates with its very own SQS queue to retrieve messages and so on, thereby providing a truly loosely coupled effect. So here, we will choose the first and most suitable option. Next, let's carefully look at question number 8. This question is mainly about a company that is currently migrating its distributed application to AWS. This application has a main server that coordinates the workloads of multiple computers. What is the variable objective here? The goal of this question is to achieve a modern architecture that provides maximum elasticity and portability. Now let's look at the 4 solutions below. First, the first solution uses SQS queues and the compute nodes use ECR, scaling based on a scheduled policy. The second option is to scale based on queue depth. The difference between these two is that both use the same components, options A and B, both use SQS queues and ECR for the compute endpoints. The key difference is in the scaling strategy. One uses scheduled scaling and the other uses queue depth scaling. So which of these two strategies is correct? Scheduled scaling is based on predictions. It cannot effectively handle variable workloads. For example, scheduled scaling might expand resources every day at noon or at 6 p.m., right? It performs scaling at these set times. Usually around the midday hours and in the late evening, the traffic volume might indeed be a bit higher, but this is just a general prediction, right? It's quite possible that even at 11:30 in the morning, there could already be a significant number of users actively accessing the system, causing a noticeable increase in activity. In this situation, if there's a sudden surge of traffic and you only start scaling at 12 o'clock, then this is actually a bit untimely, so it's not suitable. The risk avoidance solution is to scale based on queue depth. What does that mean? First, our SKS queue, as we mentioned earlier, is integrated with our components and provides asynchronicity and elasticity. Scaling automatically based on queue depth essentially means that the size of the compute nodes will dynamically scale in proportion to the actual workload. This depth refers to our actual workload. The more work there is, the more we scale. When the workload decreases, the number of instances will automatically reduce, which actually saves costs. This is the effect of our elasticity and scalability, so we should choose option B. As for options C and D, they mainly involve using ECR to implement the main server and staging nodes, and for scaling based on load using our CloudTrail and EventBridge as targets. Both of these are actually traditional single-point coordination architectures with a main server, which creates a bottleneck. This is essentially an elasticity bottleneck, because if the main server goes down, the whole system will crash. So, it's not suitable. That concludes our 8th question. Next, let's look at question 9. For question 9, we are primarily discussing an SMB file server. The various files stored on this particular server are frequently accessed in the initial few days immediately after their creation, especially large, significant files. After approximately 7 days, however, these files are then rarely accessed. Now, the amount of data keeps increasing, right? It's always increasing, and when storage capacity isn't enough, how do we solve the problem of insufficient storage? Basically, files are accessed more frequently in the first few days, meaning, as mentioned, they're accessed a lot in the first few days, but after 7 days, they're rarely accessed. So what does this mean? It means we can handle this through file lifecycle management. You can manage this by leveraging the file lifecycle, including this aspect. To ensure that new files can be accessed via DNS, and for old files, we can automatically archive them. These operations can actually help us solve and reduce some of the storage capacity issues and alleviate some of the pressure on storage. Now, let's look at a few options. Option A uses data sync to copy data older than 7 days to AWS. First of all, this is a regular data synchronization tool, which is fine, right? However, it cannot provide local users with a seamless file system view after the data has been moved. If users want to access data that has been moved, it becomes troublesome and DNS access is hard to achieve. The second option is to use S3 File Gateway and configure a lifecycle policy. First, File Gateway is actually designed for this scenario. It provides an SMB share locally to extend local storage space, and users are not really aware of it. Users do not notice anything. It automatically keeps frequently accessed data locally and stores less frequently used data in S3. At the same time, it can also use S3's native lifecycle policies to automatically move data stored in S3 to cheaper storage tiers after a certain period. This can save a lot of costs. So our second option is more suitable, right? As for option C, it uses FSX and Windows File Server. This is actually a fully managed Windows file server, but it is entirely on the AWS cloud. The performance is great, but it cannot be accessed locally, so it is not a suitable choice. Option D is to install S3 on every user device, but this actually, right? So this, although users can access it directly, right? Users are able to access it directly, but for some, large files, and when it comes to managing numerous client tools, the operational complexity increases significantly. Also, there will still be some latency if users access it directly. So, for this question, the most suitable option is the one we just discussed. Now, let's move on to question 10. Question 10 is about an application of ours. So, As for this particular application, it sends crucial information about new orders through our API Gateway REST API. The company wants to process these new orders in the exact order they are received. Let's carefully look at the available options to see which one can effectively help us process the content sequentially. First, option A is an SNS topic, right? It's something we've seen before and it's very useful, but keep in mind that it absolutely cannot guarantee the order of messages. It simply can't ensure order, and multiple pieces of data might be processed in parallel, so it's not suitable. In contrast, using an SQS FIFO queue here has the distinct advantage of strictly guaranteeing the precise order in which messages are sent and received, and each message is processed only once. This actually perfectly meets the requirements of our question, so this is not a problem. In fact, using API Gateway here is not feasible. Why? Because the authorizer is mainly used for authentication and authorization. It doesn't control business logic, so this is not correct. The first point is about using an SQS standard queue. This can indeed improve throughput, but it sacrifices the guarantee of order for performance, which isn't reasonable. Messages might be out of order and can't meet our requirements. So, for question 10, we choose option B. Alright, that's all for today's explanation. If you need the complete question bank, you can leave a comment below to purchase the most stable question bank at the best price. That's it for today, everyone. Bye-bye.